The title electrician typically brings to mind pulling high-voltage cables through residential framing or wiring commercial breaker boxes. But inside a modern manufacturing facility, the daily reality of the job shifts from basic electrical distribution to the management of high-speed digital logic. This job listing for a manufacturing site in Dandenong, Victoria, outlines the specific requirements for an industrial A-grade electrician. The text establishes a heavy technical burden. It demands a candidate capable of performing manual mechanical labor while simultaneously debugging proprietary computer code. While presented as a standard recruitment notice, these requirements provide the technical specifications for a modern industrial control environment. We parse these requirements into 3 domains: physical, sensory, and control. The physical baseline involves conveyors, motors, and hands-on fitting. Sensory terms introduce machine awareness via pneumatics, proximity sensors, and instrumentation. The digital requirements identify Allen Bradley, Siemens S7 PLCs, and the HMI. To troubleshoot in this environment, the technician must move between these 3 layers, identifying where a mechanical seizure stops a digital process, or where a code error mimics a hardware fault. To understand the nature of this role, we will reverse engineer the text and rebuild this factory environment from the ground up. We begin with Layer 1, physical actuation. This is the mechanical foundation of the manufacturing process. Here, the electric motor drives the conveyor belt to move mass, either raw materials or finished products, through the facility. The ad refers to Megger time. A Megger is an insulation resistance tester, used to ensure these high-voltage motors are safe. By pushing current through the motor windings, the electrician checks for degraded insulation that could lead to a short circuit. Hands-on fitting is necessary to physically mount and align this heavy machinery. Before any automation can occur, the hardware must be secured and calibrated. However, a motor on its own is a blind system. If a blockage occurs, the motor will continue to draw power until the belt snaps or the drive fails. To prevent this, we add Layer 2, sensing and state. Proximity instrumentation acts as the eyes of the machine. These sensors detect the presence or absence of a product as it moves down the line. This converts physical presence into a binary state. The sensor registers a 1 when an object is detected and a 0 when the space is empty. If sensors are the eyes, pneumatics are the nozzles. These systems use compressed air to perform rapid mechanical movements. Pneumatic cylinders interact with the conveyor to sort products, push items onto different lines, or halt the flow of materials when a downstream issue is detected. This creates a constant flow of raw data regarding the state of the machine. While the mechanics and sensors provide the movement and the feedback, the system still requires a central processor to interpret this data. This leads to Layer 3, logic and control, the destination for the sensor data. Industrial automation relies on the Programmable Logic Controller, or PLC. This is a ruggedized computer designed specifically to control manufacturing processes. The ad specifies Allen Bradley and Siemens S7. These are distinct operating environments with different hardware architectures. A technician must be proficient in the specific programming languages used by both manufacturers. The PLC receives binary data from proximity sensors, evaluating it against programmed instructions. This ladder logic uses if-then statements to determine how the machine should respond. Once decided, the PLC sends a command signal back down to the pneumatic actuators. This completes the primary loop. The system senses a state, processes the logic, and actuates a response. But the code inside the PLC is invisible to an operator standing on the floor. Without an interface, it is impossible to see why the machine is making specific decisions. To provide this visibility, we add Layer 4, the Human-Machine Interface, or HMI. The HMI translates the abstract data inside the PLC into graphical representations that a human can understand. It provides real-time feedback on motor speeds, system temperatures, and fault codes. Troubleshooting HMI issues involves ensuring this visual data matches the physical reality of the floor. If the screen reports a fault that isn't physically present, the technician must find where the communication has broken down. Automation functions only when the physical, sensing, logic, and interface layers are integrated into a single functional loop. We can now observe the entire industrial architecture operating as a single, continuous system. We now introduce the technician, the human variable, into this automated environment. The ADS requirement for the ability to work autonomously indicates that the technician must manage this entire environment without immediate oversight. This means they are responsible for the entire diagnostic chain. If the line stops, they must trace the failure from the physical conveyor, through the sensors, into the PLC logic, and up to the HMI screen independently. Being solutions-focused is a response to the cost of downtime. When the loop stops, the facility loses production capacity every minute the system remains idle. Beyond the technical requirements, the role includes the constraints of time and fatigue. The position transitions from a standard day shift to a rotating shift schedule after the first 3 months. Rotating shifts add significant cognitive strain. The technician may be required to diagnose complex Siemens S7 logic errors at 3 a.m., where sleep disruption increases the difficulty of logical problem solving. The mention of projects and lateral thinking suggests the role isn't limited to repair. The technician is expected to analyze the existing loop and identify ways to optimize its performance. The modern A-grade industrial maintenance role has evolved into a hybrid position. It requires a technician who can navigate mechanical hardware, digital logic, and interface software simultaneously to keep the loop moving.